bonds are formed by the sharing of electrons, right? And how is ionic bond formed? By the transfer of electrons from one atom to another. Dipole moment is expressed in the unit which is called as debye. Yes, and 1 debye is equal to 3.33564 into 10 to the power minus 30 coulomb meter. From each of the hydrogen atom, it is towards the nitrogen because nitrogen is more electronegative, and then lone pair is present means the direction will be towards the lone pair. Hello everyone, this is Ambli Unnikrishnan from the Department of Chemistry, Vidhyaashram School of Excellence, Mysore. So today we are back with session 3 of your chapter, Chemical Bonding and Molecular Structure. So in the last session, we discussed about ionic bond, the factors which were affecting the formation of ionic bond, right? And then we discussed about the bond parameters, right? In detail, we discussed on atomic radius, the different types of atomic radii, yes, and then we discussed bond angle, bond enthalpy and bond order and how they are interlinked with each other as well we discussed in last session. So in today's session, we'll be discussing on resonance structures, then bond polarity, dipole moment and finally FAJAN'S rule. Yes, so let's begin with the first topic for today, that is resonance structures. While we were discussing about the formal charge, we were discussing about the ozone molecule, right? We were trying to find out the charges which were contributed by each of the oxygen atom, right? So I hope you remember, right? A structure like this we drew, and for each of the oxygen atom we tried to find out the charge, right? So the structure that we drew there was right, this was the structure. So from this we were able to calculate the formal charge using the equation. So let's keep aside the formal charge for now. As you can see, this is one structure that is possible, right? Yes, as the same way, can I shift this double bond here? Right, if I write instead of this double bond in here, yes, that means the structure becomes like this now, okay? But the number of lone pairs will change, right? Here it will be 2 and here it will be 6 electrons and here it will be 4 electrons, right? Even this is also correct, right? All the oxygen atoms are having 8 electrons in this outermost shell. Each atom is attaining their octet. So as you can see here, these both diagrams or these both structures are correct, right? So now moving on to the diagram which I have shown here. Yes, this is one representation and this is another representation that you can see here. Yes, so what you have to understand here is that, yes, in the first structure, as you can see, the double bond is having a bond length of 121 picometer and the single bond is having a bond length of 148 picometer, right? The same ozone molecule can be represented in this form as well. Right, the double bond can be here as well as the double bond can be here. So in this structure, the double bond is having 121 picometer bond length and single bond is having 148 picometer. So as said, I hope you understood that both of these structures are possible. Both of the Lewis dot structures are correct for ozone molecule. So if I ask you to draw one single structure, which one would you draw? Is it this one or that one is correct? So in such cases, when more than one structures are possible for a single compound, we take the resonance of it. It is called as resonance structure or resonance hybrid, right? It is having the bond length which is in between it. It is neither 121 nor 148. It is not of single bond or double bond. It is having a bond length which is in between it. So this is how you can represent it. That is, the 3 oxygen atoms will be written, and then as you can see, instead of the double bonds on either side, yes, a dotted line is put up there. Yes, yes, and then a dotted line here. So the double bond can be either there or here, right? So that is the resonance hybrid. So these two structures, if more than one structure is possible for a single compound, then what do? We take the resonance hybrid of that. So I hope you understood what is a resonance structure or what is resonance hybrid. As you can see, whenever a single Lewis structure cannot describe a molecule, yes, as you can see here in the case of ozone, more than one Lewis dot structure is possible, right? Yes, a number of structures with similar energy, positions of nuclei, bonding and non-bonding pairs of electrons are taken as the canonical structures of the hybrid, which describes the molecule accurately, and this is called as the resonance hybrid. So this structure, as you can see here, is the resonance hybrid, and the number of structures which are possible, that is 2 structures are possible for ozone, right? So these 2 structures are called as canonical structures, and the hybrid that you get it from these 2 structures, that is the acceptable structure here. Yes, this is called as the resonance hybrid. Now, what is the speciality of this resonance hybrid? That it is having less energy than the canonical structures. The energy of it will be less than the canonical structures. So, less energy means more stable, right? Hence, the resonance hybrid is having more stability. Clear? So these 2 structures are called as canonical structures, and the final structure that you obtain will be a mixture of both of this, right? That is why it is represented like that. So it's called as resonance hybrid. So I hope resonance structures is clear for you. Now moving on to the next part, that is bond polarity. So to understand about bond polarity, we have already discussed about covalent bond, right? How covalent bond is formed. Is it by sharing of electrons or transfer of electrons? Covalent bonds are formed by the sharing of electrons, right? And how is ionic bond formed? By the transfer of electrons from one atom to another. So coming on to covalent bond, it is formed by the sharing of electrons, right? So let's take the example of 2 hydrogen atoms, yes, which are bonded with a single bond, right? They both need one electron to complete its duplet, right? So what happens? They share that one electron with each other. Yes, so this is okay. Now let me say I'm taking an hydrogen atom and a fluorine atom. Okay, now fluorine needs one electron, even hydrogen needs one electron to complete their octet and duplet respectively. So what do? They share the electrons. Now in this case, what you can see, the atoms are different. Yeah, right, and the fluorine is a more electronegative atom. So the shared pair of electron, that is this shared pair of electron, will have or will be attracted more towards the more electronegative atoms. That is, in the case of hydrogen and fluorine, of course, we know that fluorine is more electronegative atom. So what happens? So this shared pair of electron will be attracted more towards the fluorine. Right, so how you can represent it is H and F, this is the bond. So this is how you can represent it. That is the shared pair of electrons, it is having an attraction towards fluorine. Clear? So this is an example of a non-polar covalent bond, because there is no polarity difference here, right? There is no comparison of electronegativity here because both are hydrogen atoms. But in this case, as fluorine is introduced there, yes, an electronegativity difference happens and the shared pair of electrons will be attracted more towards fluorine. So such compounds or such bonds which are formed are called as polar covalent bonds. I hope it is clear. So, moving on to the definition, non-polar covalent bonds. When atoms are combined by covalent bonds are same, the shared pair of electron is equally attracted by the 2 atoms. As you can see here, both atoms are hydrogen. So, the shared pair of electrons will be equally shared between both the hydrogen atoms. So, such covalent bonds are called as non-polar covalent bond because no polarity is shown there. Now moving on to polar covalent bond. When covalent bonds formed between different atoms of different electronegativity, right? The shared pair of electrons between the atom gets displaced towards the highly electronegative atom. Clear? So that is what is this case. So I hope you are clear with polar and non-polar covalent bond. Yes. Now as you can see here, yes, shared pair of electrons is getting more attracted towards fluorine. So what happens is here is that the fluorine attains a partial negative charge, an extra negative charge A partial negative charge is acquired by the fluorine because what is being shared between them? It's electrons, right? So this shared pair of electrons is having an attraction towards fluorine, means fluorine will attain a partial negative charge and hydrogen will be attaining a partial positive charge. Yes, so now as you can see here, a partial positive and negative charge, that is two charges are separated by a distance. Now what is that? When two charges are separated by a distance, some new term is being introduced which you have already studied in physics. Yes, it is called as a dipole, right? Yes, two charges separated by a distance, right? So associated to that dipole, a dipole moment will be there. So you already have studied this in physics, how to calculate dipole moment. Yes, dipole moment is defined as the product of magnitude of the charge and the distance between the charges, right? It is equal to the charge, that is charge present on the atom, multiplied by the distance of separation. Yes, the distance of separation between these two charges. So that gives you the dipole moment, which is represented by the symbol mu. Okay, now the unit to represent it is dBA units. Dipole moment is expressed in the unit which is called as dBA. Yes, and 1 dBA is equal to 3.33564 into 10 to the power minus 30 coulomb meter. So I hope it is clear. So this is about dipole moment. Yes, we know that two charges, when it is separated by a distance, a dipole, that is what we call it as a dipole, right? So associated to that a dipole moment will be there, which we can calculate it using this equation, right? So as you saw in the case of HF, right? How the dipole can be represented? Yes, the direction is in this way, right? So the head of the arrow should be towards the more electronegative atom. In this case, it is fluorine. So the head of the arrow will be here and the positive sign, that is, as you can see, a positive sign is here, right? So that will be towards the atom which is attaining a partial positive charge. That is, in this case, hydrogen, right? So this is dipole moment, and as you can see, it is a vector quantity. Why it will be a vector quantity? Yes, it is having a particular direction as well, right? Yes, it is attracted towards a particular atom, so it is associated with a direction as well. Clear? So it is a vector quantity, means the magnitude and direction is of importance, right? So now when we are moving into polyatomic molecules, right, if more than one atoms are present, in this case only these two atoms are there, so we know that the dipole is in that direction. But if more than one, like many atoms are present, polyatomic molecules, right, how do we calculate the dipole moment? We are going to see that in polyatomic molecules, the dipole moment not only depend upon the individual dipole moment of the bonds, but also the spatial arrangement of various bonds in the molecules. Yes, so in polyatomic molecules, many directions will be present, right? Between each bonds, the dipole moments associated with each bonds will be different. Yes, so the spatial arrangement of each of these bonds should also be considered, not just the individual dipole moments. Yes, we have to calculate the overall dipole moment, right? So just by looking onto the individual dipole moments and just adding it will not give the answer. So how do we calculate it? The dipole moment of a molecule is the vector sum of the dipole moments of the various bonds. As I just said, it is a vector quantity. So how do we calculate it? It is the vector sum of the individual dipole moments. Clear? So let's take the example and understand it, right? So as you can see, first example is BeF2 molecule. So as you can see, one Be atom in the middle and fluorine on either side. Yes, so among beryllium and fluorine, which is more electronegative fluorine, right? So the dipole moment of this bond will be towards that direction and the dipole moment will be towards this direction in this case, right? I hope it is clear. The fluorine atom are on either sides. Yes, we know how to represent the dipole moment as well, right? From the less electronegative to the more electronegative one. Yes, so the direction will be here and here. So as you can see, both are in opposite direction. So what happens? The net dipole moment will be 0 here. They cancel out each other. Right, one towards that direction and one in this direction means they cancel out each other. So the net dipole moment will be 0. Now moving on to water. Yes, as you can see, there is one oxygen and two hydrogen atom. It's represented like this. So we know that out of oxygen and hydrogen, oxygen is the more electronegative one. So the arrows will be heading towards oxygen, right? So one in this direction and one in this direction. So do they cancel out each other? No, right? So they will be having a particular dipole moment. Now moving on to the next example, that is BF3, right? So in the case of boron, it is in the center and there are 3 fluorine atoms. So as you can see, comparing boron and fluorine, fluorine is of course the more electronegative one. So one dipole moment in this direction, one in this direction and one in this direction. Right. So as you can see, the one is in this direction. Now what about these two? One in that direction and one in this direction means the resultant of these two will be also in this direction. That is what is shown here. The resultant of these two directions that can see these two bonds, the resultant of these two dipoles will be in this direction, which will give a net dipole of 0. Now you can see these two cancel out each other, right? In this case, it is not cancelling it out each other. So what you can see, this is a polar molecule, right? Water is a polar molecule because it is having a certain dipole moment. So I hope it is clear how to represent it and how did I calculate the net dipole moment as 0. Yes, the resultant will be also in that direction so that it cancels out with each other. So this is about how you can calculate the dipole moment of polyatomic molecules. So now moving on to an example which is a special case and which is of very importance. Yes, so let's see. Yes, here NH3 molecule, that is ammonia, and NF3 is present. Okay, so seeing the two molecules, that is NH3 and NF3, what can you predict? Which one will be having more dipole moment? Yes, from comparing nitrogen and hydrogen and nitrogen and fluorine, yes, fluorine is having more electronegativity. Fluorine is more electronegative atom. So what would be the prediction or what would be your answer? Yes, NF3 will be having more dipole moment. But this is not correct. Yes, comparing NH3 and NF3, that is ammonia, is having more dipole moment. So let's see why exactly this is happening. Even though fluorine is the more electronegative atom, why is ammonia having more dipole moment? That is why it is a special case, right? Why it is happening, let's say. So comparing nitrogen and hydrogen, nitrogen will be more electronegative, right? So as you can see, the direction will be towards nitrogen. And on nitrogen, we know that an electron pair is also present, right? Yes, an electron pair will be present. NH3 means, right, one lone pair will be present there. So considering the dipole moment in this part, yes, it will be towards the lone pair, right? From nitrogen towards the lone pair. So the direction will be towards the lone pair. Right. So from each of the hydrogen atom, it is towards the nitrogen because nitrogen is more electronegative, and then lone pair is present means the direction will be towards the lone pair. Yes, lone pair is considered as the more electronegative one. So it will be towards the top. Right. So the resultant of this will be towards the top, right? Yes, all of these are towards nitrogen, and even nitrogen to lone pair also is towards the top. So the resultant will be added, right? All of this will be added and it will be towards the lone pair. Clear? Now what about NF3? We know that comparing N and F, that is nitrogen and fluorine, fluorine is more electronegative. So the dipole direction will be towards fluorine. But in this case, from nitrogen to lone pair, it will be towards the lone pair. So what happens? These three are in this downward direction. Yes, and from the nitrogen to lone pair, the dipole is towards the lone pair. So that is in this direction. Now one towards top, one towards down. So what happens? It cancels out each other, right? Yes, it won't be 0 because as you can see, 3 bonds, NF bonds are here and only one electron pair is there. One lone pair is there. So it won't cancel out each other, but the value will be decreasing because yes, one towards top and one towards bottom means yes, it will cancel out each other. So in this case, what happens? The net dipole moment will be less. right? Because it is getting cancelled out to each other. In this case, it is getting added because all of them are towards one direction. Here, the dipole moments of the NF bonds are towards down, and the other one is towards the top. So it cancels out each other. So the resultant moment of the NH bonds, right, add up to the bond moment of the lone pair, whereas that of the three NF bonds partially cancels moment of the lone pair. So the dipole moment of the lone pair is towards up and it cancels out each of this. So in this case, the dipole moment of the lone pair adds up to the dipole moment of each of this NH bonds. Hence, what you have to remember, ammonia will be having more dipole moment than NF3. It's not the other way. So I hope this special case is also clear for you. Yes. Now moving on to the next important topic, which is FAJAN'S rule. So why exactly we are studying about FAJAN'S rule is that we have studied about covalent bond and ionic bond. Right. Yes, covalent bond, sharing of electrons, and ionic bond is formed by the transfer of electrons. Right. We are very clear about that. So what you have to understand is no covalent bond is completely covalent. That means in a covalent bond, some amount of it will show an ionic character as well. And in the same case, the ionic bond will not be completely ionic bond. Even that will be having a little character of covalent. That is, it is having a covalent character. So as you can see here, all covalent bonds have some ionic character. Same way, ionic bonds also have partial covalent character. So in FAJAN'S rule, we are going to study, yes, how much of this covalent character will be present in an ionic bond and how much of ionic character will be present in covalent bond. So what you have to understand is no covalent bond or ionic bond is completely covalent or ionic. It will be having some characteristics of the others as well. So clear? Yes. So when a cation approaches an anion, the electron cloud of the anion is attracted towards the cation and hence get distorted. This is called as polarization of the anion. So we are going to see what exactly is happening in here. How you can conclude that there is a covalent character in ionic bond we are going to see. So we know that ionic bond is formed between an anion and a cation. So we are considering a cation here and an anion here. So if they are present at a distance, no problem. If they come closer, yes, closer and closer to each other, what happens is in cation we know that it is a positively charged ion and anion is negatively charged ion. And in anion, yes, in the outermost shell, the electrons will be present. So when the cation comes near the anion, what happens is the electron cloud of the anion is being attracted towards the cation. We know that positive and negative charge, right? So the cation is having a positive charge. That means the electron cloud of it will be attracted towards it. So this, as you can see here, it was a spherical shape before. Now it gets distorted like this. That is what is represented here. The shape is changing, which means that the electrons are being attracted towards the cation. So that is what is written here. It is attracted towards the cation and hence get distorted. Yes, the anion gets distorted. The shape changes. And this is called as polarization of the anion. Yes, when the cation comes near the anion, yes, what happens? The electron cloud is attracted towards the cation. Yes, and what happens? The anion gets distorted. This is called as polarization. So this process that is happening here, this is called as polarization. Right. Now moving on to polarizing power. The power of cation to polarize the anion is called as polarizing power. Yes, polarizing power is present in cation, right? When cation comes near anion, it is able to attract the electron cloud. So the polarizing power will be with the cation, right? So the power with which the cation is able to distort the anion is called as polarizing power. And now one more term is there. What it is? Polarizability. Now what is polarizability? It is the tendency of anion to get polarized. Yes. So cation is having polarizing power. Now what is anion having? That is polarizability. Right. The tendency of anion or to how much extent the anion is getting distorted, that is called as polarizability. Yes, and this whole process that is happening is just called as polarization. Yes, so what you have to actually understand here is that greater the polarization, more is the neutralization of the charges and less is the ionic character and more is the covalent character. Now, what is exactly happening here? As I said, when the cation comes towards the anion, the electron cloud is being attracted towards the cation. Now what happens? Positive and negative charge, right? They start neutralizing with each other. Positive and negative charge coming closer, they start neutralizing with each other. And this neutralization of charges means the ionic character will be becoming less and less, right? Ionic character means how an ionic bond is formed by positive and negative charges, right? Yes, ions. Right. So what is happening if the charges are neutralizing? That means ionic character will be becoming less and less. Now what is being increased? Covalent character will be increased. Why? Now the electrons are starting to share between them. Right, because the anion is being distorted and they start sharing the electrons with each other, which increases in covalent character. So what you can understand from here, this bond that is formed between them, it is not completely ionic bond. What happens because of the polarization that is happening here? Yes, it is having some covalent character as well. Yes, so I hope what exactly is happening here, it is clear for you. Yes, polarizing power, polarizability and polarization is clear for you, I guess. Now, moving on to the factors on which this polarization depends, let's see. So, smaller the cation, greater will be the polarizing power. So, polarizing power, what did we study? The power of cation to polarize the anion. So, smaller the cation. Smaller the cation means, we know that if the size is small, that means the nucleus and the outermost electron will be very close to each other, right? Size will be less means, I am considering this, the size will be less means they are very close to each other. So what happens? Smaller the cation means size will be less. That means greater the polarizing power. So now the size is less means the attraction will be very more. So polarizing power of cation will be very more in that case. So what happens? It can easily polarize the anion. Right, polarizing power is increasing because the size is decreasing. Right, so what happens? Easily it can polarize the anion. So smaller the size of cation, greater the polarizing power. Now larger the size of anion, greater the polarizability. Now how is that? Larger the size of anion means, yes, size is increasing means the outermost electrons will be loosely bound with the nucleus, right? The attraction will become less and less when the size is increasing. So what happens? The outermost electrons are loosely bound. So if a cation is brought near that, or if a cation approaches near the anion, already the electrons are loosely bound. They will easily get attracted here and easily the shape of the anion will get distorted. So what you can say, larger the size of anion, what happens? The polarizability of the anion increases. Right? Yes. Now moving on to the third one. Larger the charge on cation, greater its polarizing power. So larger the charge on cation means the size will keep on decreasing. The charge on cation is more means, yes, for +1 charge means 1 electron is being removed. So what happens? The size again decreases because less number of electrons, the effective nuclear charge will remain still the same. So what happens? More and more pull will be towards the nucleus. So what happens? The size again decreases. So what we have studied about the relation, smaller the size, greater the polarizing power, right? So what happens? Yes, when the charge of the cation keeps on increasing, the size will get reduced. That means the greater the polarizing power. Now moving on to larger the charge on anion, greater will be the polarizability. Larger charge on anion means more and more electrons is getting added. Charge on anion means we know that it is negative charge, right? So if it is -1 means 1 electron is being added on to it. -2 means 2 electrons are added on to it. That is how an anion is formed, right? So more number of electrons means, yes, what happens? The attraction between them will get less and easily they can be polarized. Yes, polarizability means what? The tendency of anion to get polarized, right? So larger the charge on anion means, that is larger the charge on anion means the size is keeping on increasing. That means easily they can be polarized. That in a way we can say that greater will be the polarizability. Now let us take a condition or let us take a situation where 2 cations are present and I have to polarize a single anion. 2 cations are present and they are both having same size and charge. We know based on size and charge how we can consider which cation will be having more polarizing power, right? So now I am considering 2 cations which are having the same size and charge. Now, how do I confirm which one will be having more polarizing power? Yes, if same size and charge on cations, then the one with electronic configuration of transition metals is more polarizing than one with noble gases alkali or alkaline earth metal cations. Yes, if two cations are having the same size and same charge, what do we have to see is their electronic configuration. If the electronic configuration of the cation is that of transition metals, we know that they are d block elements, right? If d orbitals are present in there, yes, they belong to the transition metals. So, now we have to consider the electronic configuration. If the electronic configuration of the cation is that of transition metals, they will be having more polarizing power. Why is that? Is because, yes, the d orbitals, yes, are having less screening effect. The screening effect of d orbitals are very less. That means, yes, now the nucleus and the electrons are having a good interaction with each other. The screening effect is less means the other inner electrons present in it will not be able to screen the outermost electron in a good way. That means the attraction between them will be very high, right? If the screening effect is more, that means the inner electrons is not allowing the nucleus to give its full attraction to the outermost electrons. Yes, we have already studied about screening effect, right? So, if the screening effect is less, that means the attraction between the outermost electron and the nucleus will be more. So, in that case, what happens? The polarizing power will increase, right? The size is reducing. Yes, because the attraction is more means with more pull, the outermost electrons are pulled towards the nucleus. So what happens? The polarizing power increases. But coming on to into the case of S and P block elements, their screening effect is more. For S and P block elements, the screening effect is more. Screening effect is more means they are not allowing the nucleus to completely attract the outermost electrons. So what happens? The power or the polarizing power of those cations will be less. So what you have to remember is that if same size and charge are present on two cations, based on the electronic configuration of the cations, we can decide, yes, which one will be having more polarizing power. The transition metals will be having more polarizing power. The cation having electronic configuration that of transition metals will be having more polarizing power than the S and P block elements. Clear? Yes. So this is about FAJAN'S rule. So I hope it is clear. So in the next session, we will be discussing about the next theory on chemical bonding. Yes, we started this discussion with Cousins-Lewis approach, right? Now the next one we will be studying in the next session, that is VSEPR theory, that is valence shell electron pair repulsion theory. Yes, wherein we'll be studying in detail about the shapes of the molecules, right? So the geometry of molecules with only bond pairs and with lone pairs also we will be studying, and then as well as the limitations of VSEPR theory we will be studying in the next session. So I hope what and all we have discussed in this session is clear for you. So that's all for today. Thank you.